So going to be talking about the neurobiology of burnout. And I want to emphasize right from the start, this talk is based on a paper I wrote with Tate Shatterfeld. And he is the expert on burnout itself. He's at Stanford. I'm the neurobiologist. So if you have questions about burnout, unless I've heard him say the answer, he might be the better person to talk with. So about half of American physicians reported experiencing burnout before COVID. So already a remarkable number. And burnout is an occupational syndrome. And this is something Tate always wants us to emphasize. It is resulting from chronic occupational stress. It's formally recognized by the World Health Organization as an occupational syndrome. And he really likes us to emphasize this. By definition, occupational burnout is primarily precipitated by characteristics of the work environment rather than by the individual. So it's not that the individual is not resilient, strong, it's that the work environment is toxic in ways that creates this. And so it's changes in the work environment then that are needed to reduce risk primarily. And this is something that his whole career is based on. So what is burnout? It includes both emotional and cognitive changes, such as emotional exhaustion, depersonalization, or cynicism, diminished feelings of personal efficacy and accomplishment, and a lot of impairment in cognitive abilities, such as impaired working memory, organization, concentration, which we'll get at in a moment. There are also physiological changes with increased risk of a lot of cardiac symptoms, such as hypertension, atrial flutter, and also depression and even suicide. So can have very serious consequences if not dealt with. So burnout often arises due to a lack of control. And this can come from excessive administrative burden, too many hours at work, which of course happened during COVID and lingers due to reduced staffing, increased computerization and electronic record commands, and lack of respect from administration staff, and feeling like you're just in a cog in a wheel without any self-efficacy. So what I'm hoping to do in the next few minutes is teach you about some of what we've learned about what uncontrollable stress does to the brain and why then it can produce these symptoms of burnout. Because many of us feel that when you've learned the neurobiology, it really helps you have understanding and perspective that can promote self-efficacy and in particular stop the vicious cycle of self-blame. So decades of research in both animals and humans have shown that the key factor in whether stress has toxic effects on the brain or not is whether the subject feels they have control over it. So it can be an enormous challenge, but if you feel you're confident and in control, these toxic stress responses don't happen. Conversely, it can be something quite minor, but if it freaks you out, it has these effects on the brain. And the work of Steve Mayer, if anybody's interested, really pioneered a lot of this in rodents. So many changes in medicine have, of course, eroded self-control over people's practice, increased pressures from insurance companies and electronic records, financial pressures from debt, patients expecting much more now that they hear about miracle cures on the internet, and of course, the intense workloads where you really are overwhelmed and you're cognitively correct in assessing that there is too much need for what you're able to handle. So research in animals and in humans has shown that this uncontrollable stress weakens our recently evolved prefrontal cortex, and at the same time strengthens our more primitive circuits in the brain. And these primitive circuits mediate habits, emotional responses, instinctive responses. So it can very quickly put the brain into this much more primitive state with an erosion of top-down control of our attention, our actions, and our emotions. And did anybody learn about prefrontal cortex in med school? Did all of you go to Yale Med School? That means, or Yale College. Because when I ask this of residents very often, they say no, they hear very little about it. And yet it's like a third of our brain. So important very much to know about this region, which is right under our forehead and then proceeds caudally to the motor cortex. So the the discovery about prefrontal cortex and cognition occurred in this very building. It began here 100 years ago. So this is very much a Yale story. Carlisle Jacobson is the one who discovered that if you make lesions of prefrontal cortex in monkeys, it profoundly impairs working memory. And he said it's as if out of sight, out of mind were literally applicable in these animals, and it was a permanent disability with those lesions. And then decades later, Pat Goldman-Rakish, again in this very same building, discovered the neurobiological, the cellular basis for these abilities, where she found circuits that can generate and sustain mental representations, for example, of point in visual space, without any sensory stimulation, which is the foundation of abstract thought and top-down control. And this is one of her famous neurons that is firing to the memory of stimulus that had occurred in this spatial location, but didn't fire if it was presented in any of these other locations. So dedicated firing in spatial working memory. And what she also discovered is this ability of prefrontal neurons to represent information without any sensory stimulation was due to their ability to excite each other, something we call recurrent excitation. So they're able to excite each other without external inputs. And this is something that increases hugely over brain evolution. So these are dendritic spines where a lot of these recurrent connections and other connections occur. In the primary visual cortex, all primates have about the same number of connections. But here in the prefrontal cortex, I know you can't read any of this, but we have baboon, marmoset, macaque, and human at the top. So it's this huge expansion in the numbers of connections in these prefrontal areas. So allowing for so much more information then to be kept in mind. So here are some examples of functions carried out by prefrontal cortex. And as I said, this is a huge part of the human brain, so it's not surprising that it does so many important things. Higher reasoning and abstract thought, higher order decision-making. In humans, language production, which in right-handed males is localized to the Broca's area in the left hemisphere. Working memory and concentration. Planning and organizing for the near and farther future. Insight and judgment about ourselves as well as others. And really important in challenging times in medicine, hope and optimism and being able to persevere through difficulty. Empathy and moral conscience are part of the frontal pole in particular, and being able to inhibit inappropriate impulses, habits, and emotions that are generated by more primitive circuits often. So the prefrontal cortex provides this top-down, thoughtful, and flexible regulation over cognition, action, and emotion. And this is through topographically organized circuits that are really quite extraordinary. But just in general, to let you know, the medial surface of the prefrontal is especially important for governing emotion. And it has connections out to the limbic structure that mediate our emotional and visceral responses. So, for example, the amygdala, which initiates much of our emotional responses. The basal ganglia, the striatum, caudate putamen, which mediates habitual responses, things that we've learned to do from repetition, and also instinctive responses, especially, for example, in birds. And then the hypothalamus and brainstem for control of the autonomic nervous system in particular. So dorsolateral prefrontal, these higher cognitive circuits, have extensive connections to the medial areas to then provide this top-down control of emotion. And one of the important things in medicine is they can control the emotional response to pain. So as many of you might know, there are parallel pain pathways where the medial pathway, the one coming from the medial thalamus, is the suffering part of the pain pathway. And that comes up to the anterior cingulate, down here to the subgenual cingulate, out to the amygdala and the autonomic nervous system. And this pathway is regulated very much by prefrontal, our ability to reduce the emotional suffering aspects of pain. And what happens in depression is we lose this top-down prefrontal regulation, and subgenual cingulate in particular becomes overactive and is now the target of deep brain stimulation for the treatment of intractable depression. So prefrontal dysfunction is a contributor to many different neuropsychiatric disorders. Basically, if we call it psychiatric, it's because there's prefrontal dysfunction is my way of looking at it. And if anybody is further interested in this, I actually made a YouTube about this that's on the Yale Medical School YouTube channel, because it really helps explain a lot of the neurobiology underlying many of these disorders. So dysfunction of prefrontal cortex also occurs in all of us in daily life due to fatigue or exposure to uncontrollable stress. I should note, though, that the prefrontal is also one of the key regions for turning off the stress response. So it's what's saying, we're okay, we're in control, don't worry about it. And it has projections down to brainstem to actually inhibit the stress response. But it itself is remarkably sensitive to our state of arousal with this very narrow inverted view. So all biological systems have an inverted view, but what's extraordinary here is how narrow it is. Real Goldilocks has to be just right. So under conditions of fatigue or uncontrollable stress, we have impaired prefrontal function compared to when we feel alert and safe. And we're actually have prefrontal offline, for example, during sleep. And you can see this in human and animal studies with fMRI. You can see the weaker prefrontal connectivity with fatigue and impaired function, and conversely the same thing with stress. Many studies have now shown that you can, in a lab, try and produce an uncontrollable stressor and see prefrontal cortex becoming underactive. So my lab has been studying how this happens and the great sensitivity of prefrontal cortex to the arousal modulators, norepinephrine, dopamine, acetylcholine. And the recurrent excitatory circuits I told you about before arise from glutamate axon terminals releasing glutamate onto dendritic spines. And at these synapses, they're very unusual. They are almost wholly dependent on NMDA receptors rather than AMPA receptors. And NMDA receptors have unusual properties in that they only work if they're sitting in an electrified membrane. And normally AMPA receptors do that electrification. But in prefrontal, this special property is done by acetylcholine. And the reason this is so interesting and relevant to what we're talking about today is acetylcholine is only released during waking, not during deep sleep, which helps to explain why we're unconscious during deep sleep, because then these can't connect. But acetylcholine release is decreased by adenosine, which builds up over the course of the day and inhibits cholinergic cell firing. And this is how coffee works. This is how caffeine works. It inhibits adenosine actions and allows cholinergic actions, and thus allows connectivity here. So this is part of the normal fatigue and alertness that I'm certainly doing right now. Conversely, we've learned a whole lot about how stress can impair prefrontal function. And with an acute, uncontrollable stress, this can happen in just a moment. And how it happens is that this huge release of catecholamines in particular creates feed-forward cyclic AMP calcium signaling, which then opens these potassium channels right on the spines and shunts out the network connection. So you're instantly disconnecting these recurrent circuits. At the same time, high levels of catecholamines actually strengthen these primitive circuits. So they make amygdala, striatum more effective. So you're doing this big shift from a reflective to a reflexive state. And the catecholamine actions are boosted by cortisol, although cortisol is a slower response. But for example, cortisol blocks the transporters that normally suck out catecholamines from the extracellular space, and cortisol can also increase catecholamines intracellular action. So they work together to impair prefrontal very rapidly. And you could see where this mechanism could be very helpful, have survival value when we're in danger. So for example, you're driving along 95, planning this grant you're gonna write in your head, and you're suddenly cut off by a big SUV. You don't think, okay, this is a large SUV, it would be helpful if I put my foot on the brake. You just slam on the brakes. You stop thinking about your grant, and this habit just kicks in. And under those kinds of conditions, you can see why this is life-saving, why this mechanism has carried on for millennia, from certainly rodents to us. But if that threat and danger is something much more complex and you need your prefrontal to solve it, for example, taking care of a patient with something unusual, and for many people, just being able to imagine what a virus is, you need your prefrontal to survive and thrive. And with chronic stress, we actually lose these connections. I should say the cell body remains, but we lose the spines and axon terminals and even the dendrites. So this atrophy. And this was a study showing that you could get weaker prefrontal connectivity even in medical students. So this MD PhD student for his thesis studied his fellow students as they studied for the boards for step 1, and found that they developed weaker prefrontal connectivity that correlated with impaired prefrontal cognitive abilities. But as we'll see, luckily, with time spent unstressed, the connectivity returned. So in contrast to prefrontal that's losing its dendrites, in the amygdala, the dendrites actually expand. So we get these architectural changes that make these differences in brain state from reflective to reflexive even more obvious. So as I just mentioned, thankfully, research in rats and humans shows that with time spent unstressed, these connections can regrow. I should say that in the older rats, there seemed to be less of it, but I like to think it's just because they didn't wait long enough. But there is plasticity in this system, and why a vacation, for example, might be so important. So brain changes in burnout, we can see very similar to what I've been talking about. There haven't been that many studies of actual human subjects undergoing burnout, and they weren't done in physicians, but they show prefrontal atrophy, very similar to what's seen with chronic stress. And in particular, the reduced thickness of the prefrontal cortex correlated with the impaired ability to downregulate negative emotions, so not being able to control your emotional state. And excuse me, it correlated with perceived stress by the subjects. And subjects with occupational burnout also had to overactivate their prefrontal in order to perform a cognitive task at the same level as control subjects. So having to engage more and more cortex, which I more tiring. So this is a list of things that Tate came up with relating prefrontal dysfunction to what it would do to medical practice. And so the forgetful concrete thinking and the potential for medical errors, difficulty concentrating and being disorganized, harder to manage complex tasks, which is so much of medicine. Impaired decision-making, obviously suboptimal care and medical errors. Reduced insight, judgment, and moral conscience, decreased commitment to professionalism. Decreased empathy and compassion, so impaired communications not only with patients, but also with coworkers, which can make work environment worse. Decreased optimism and persistence, so the cynicism and decreased engagement. And decreased self-regulation and inhibitory control, where that increased likelihood of unprofessional behaviors. So how to help yourself if you are experiencing symptoms of burnout. First, what does not help, but which is what we all mostly first reach for, things like alcohol can give this short temporary relief, but in the long run make things worse, not only by tolerance and withdrawal, but alcohol itself on a regular basis further erodes prefrontal structure and function. Same with benzodiazepine and other addictive habits. So what's helpful? One of the key things to stop the vicious cycling of, oh, I'm so stupid and I should be strong enough to deal with this, and this shows that I'm an inadequate person, is don't blame yourself, to realize this is the normal biology, and it's just that we are mammals. Trying to restore a sense of control by making changes, or if that's not possible, by working with others to advocate for change, trying to have that sense of control if you can, and why administrators partnering and creating teams can be so important for the mindset. The prefrontal cortex needs constant glucose and oxygen. That recurrent excitation is very energy intensive. So eating healthy snacks, not something where you're going to spike your sugar, and exercise can really help to stay online. Prefrontal is preferentially enhanced by exercise, as long as it's not too exhausting. And engaging in activities that are meaningful and refreshing and provide perspective, because perspective gives you a sense of control. Things like social supports, music, and the arts, meditation and mindfulness have been shown to be able to enhance prefrontal function. And really important, if the feelings of burnout are serious, to have a really low threshold to go get help. Because, for example, SSRIs can shift the brain back into a healthy state and shut subgenual cingulate off. So help can really bring one to a more normalized state. And there's many resources online. Here are two of them. Are you guys going to have this? Well, it's recorded. So if you're needing those sites. So thank you very much. And are there any questions? I threw a lot at you in just 20 minutes.
That was really cool. I miss all the neurosciences that you called. Speaking of like phineas gauge, when you have to pipe through his prefrontal cortex.
Yes.
Cool. What do you think, like when we, surgery residency, like one of the big goals I feel like is we have to learn how to deal with pressure and stay calm. Like that's one of my goals. But I think sometimes I think, well, I got to put myself in very stressful situations repeatedly to get that, skill to maintain your composure. How do you reconcile that? Because in one sense, you're saying, well, throw yourself into as many stressful situations as you can to build that up.
So this is how you build confidence. Yeah, I'm hoping that you're throwing yourself into stressful situations, but with safety nets, so that when you're first learning it, there's somebody there who can help. And that's where the teamwork, I think, is so important. That yes, you set up yourself with the help, and then when you're feeling confident enough, then you're helping someone else. It's how things are supposed to work in medicine. But very much that repetition, and also the basal ganglia learns by repetition. So developing these healthy or effective habits, whether it's surgical or not. So you're knowing what to do even in an emergency situation. This is what boot camp is in the military. It's a lot of what medical training is, so that you're not having to suddenly invent the wheel under a condition where things have gone suddenly wrong. So that can help too. But yes, making oneself immune is very much by having the repeating stressful experiences, hopefully with support, hopefully doing well with it so that you do develop confidence. Because of course, it can backfire if you do it disastrously, right? So I remember with public speaking as a grad student, I did like this and made myself do it over and over again. So now it's just fun.
Related to that, this is an age-old question and probably not an answerable question right now, I would guess, but do you think, for example, the surgeon has to be able to get into a major bleeder, it could be life-threatening, be able to control that. And so you have to learn to deal with stress and be able to think your way through that problem. Do you think that there are people who are born a certain way to do that? They're wired, their connectivity is a certain way? Or do you think it's probably a little bit of both, but do you think that they're trained and can learn to be good at that?
I think it'd be both. And so certainly the training, I mean, part of it is you've been trained to know what to do when that person's bleeding out, right? If you were having to solve it for the very first time, you'd have a very different experience of it compared to people having taught you things that you can do under those conditions, and have a bag of tricks that you can turn to. But we also know that, for example, genetics, the COMT genotype, COMT is the enzyme that destroys catecholamines. And so in some people, they have a thymine substitution for valine, which makes the enzyme much weaker. So those people have higher levels of catecholamines. And they perform better under normal conditions, safe conditions, but have a lower threshold for stress-induced impairment. Whereas conversely, on the inverted view, the valine guys have a little catecholamine under normal conditions, but perform better under some mild stress given in the laboratory. So things like that probably contribute. Also, things like lifetime stress experience, including early childhood, severe adversity can really affect the prefrontal architecture, so the buildup of that over time. Also, why you can see where burnout itself, if you're having to work onerous hours for years and are losing prefrontal gray matter from the stress, that you're not going to be as well equipped to deal with situations where you're needing to have flexible thinking and decision making on the spot. Hopefully you've had the experience so that you can fall back on those habits.
Well, like one thing Malcolm Gladwell's had that like 10,000 hour rule. Has anyone studied like in terms of prefrontal cortex, like if you do a surgery 1,000 times and that's at the expense of your sleep and well-being versus doing it 500 times, but being maybe well rested, like I don't know what's better. I mean, because it's either one or another. I mean, is it better to just do something a lot more at the expense of kind of, your time, or is it better to be more optimal for it?
I think it would depend on how stereotyped the surgical experience was going to be. So if it was the type of surgery where it was you knew what to expect, you could really rely on past experience, then having a more tired, burned out prefrontal would be okay. If it's the kind of surgery where unexpected things happen and you're having to come up with solutions on the spot, that's when you're going to want prefrontal. So, and my guess is you guys have a sense of that. If it's a surgery you've done many, many times, you can be more tired. I mean, we have the same, we're not doing surgery, but it's that same thing of, I've given this lecture on the basal ganglia 6,000 times, so I can do it, versus, oh my gosh, this new lecture on the classroom, and I remember what the classroom does. You can see how the basal ganglia and this, you can even do things unconsciously with basal ganglia. They save us tremendous energy. It's this automated programs spit out, and that's a saving grace as long as what it's programmed to do actually works in that particular situation.
I think it's important to differentiate between a stressful situation like a bleeder or like an acute case or something where you're slapping on the brake and state kicks in and like all the lights are going at once and you kind of wake up from that. And then some of the low-level stress situations, like you're tired, you had a long day, and there's a challenging patient or something that needs a little bit extra empathy from all that. And it's hard, you're not slapping on the brakes or whatever, swerving, avoid lack of empathy, but you need to kind of really have your resources available to deal with those kind of situations as well, which also takes practice and taking a step back before avoiding the patient's room and to develop or this is a separate situation. I think those are actually the not life-threatening challenging, but those are the real challenges we face on a day-to-day basis that don't get addressed.
Which Tate really emphasizes. And we also relate to monkey behavior. So why do primates have these huge prefrontal cortices? Because for us, a lot of threat comes from our non-specifics, that we have social cognition as such a major part of our survival and thriving in, and the tremendous complexity of human social relationships. And in the case you're describing, where you're the benevolent person in power, or you're supposed to be, even though you're feeling really pissed at them, that we're totally needing prefrontal.
The background for my question is, it sounds like you were saying if you're in a chronic stress place and you remove yourself from that for a long period of time, there are structural changes in your brain. If you're in a stressful situation and you go on vacation for a week, it's restorative, you feel better. Is that a short-term thing that you feel better and maybe less, like you put up adenosine for a week, but there's no real structural changes? Or are there studies that show even in a short period there can be structural changes in the brain?
The studies in rodents where they actually image spines, that they can come back even within a day. But so I think it would be a factor of how long they've been gone, how old the subject is. Unfortunately, so at least that was true with the rats, where there was less plasticity in the oldest rats. And also what the previous history. So if you have had a history of many diverse experiences, including childhood trauma, it might be harder for those to come back. But the rodent data at least suggests that it can happen relatively quickly. And then I also want to stress the chemical mechanisms, which are very rapid. So I now see this in myself constantly. I've opened my email and see that a paper is rejected, and within 2 seconds, I feel my prefrontal offline. This flood of catecholamines can really have disconnect very quickly. But conversely, you know, I shouldn't say daiquiri on the beach when I just said no alcohol, but it's such a symbol of relaxation, right? That can put one in a neurochemical state that's optimizing connectivity. And that's why our discovery of guanxine, which is granulates in tuna, it helps strengthen those connections. And so it's mimicking a safe neurochemical environment. It hasn't been tested in burnout, but it's being actively tested here for cognitive deficits in long COVID. I say that because so many people have it and it's so devastating.
I have a question on that. I asked how to increase brain blood flow.
How does what?
How to increase brain blood flow.
Exercise. There's actually several studies showing that exercise, not exhaustive exercise, but that it preferentially enhances the bold response in prefrontal cortex. And that might be related to this increased need for oxygen for the current fire. So part of why exercise might also be antidepressant. So I think that would be the simplest answer to that. Thanks, everybody.